Hello, good morning. So let's get started with our warm up for today. What I have here is I have a motionless system here where the ramp and the pulley are frictionless. So there's no friction here, but the system is motionless. In other words, it's in equilibrium, it's not moving. So what I want you to do is I want you to figure out the mass of the block B. So basically you have one block that's on a ramp, the 200 Newton block, and then you have another block that's block B that's attached to it via a rope and pulley. And so I want you to figure out what is the mass of block B. And then what I want you to do is I want you to figure out how does this answer change if the angle is increased to 70 degrees. So for those who are just joining us today, what we have here is we have a ramp and a pulley in a motionless system. So the system is in equilibrium. There is no friction here as well. So what I want you to do is I want you to figure out what is the mass of block B that is needed in order to keep the system motionless. And then what I want you to do is I want you to figure out how does this answer change if the angle is increased to 70 degrees. So I'm going to start going through this problem here. Start doing this step by step. So this is probably one of the first. We might have done one other one, but this is one of the first double object problems that we've encountered. And so when we're working with a double object problem, we are going to want to do everything essentially twice. So we're going to need to draw two free body diagrams, and we're going to need to solve like two sets of equations essentially in order to figure out what we need to figure out for this problem. So what I drew here is I just drew the diagram again. It is attached another block. So the first thing we want to do, as always, is to draw a free body diagram. Now there are two objects in play here, which means we should draw two free body diagrams to help us visualize what's going on with each one. So the first one, let's just first start with the block B. Block B is pretty easy. There's just two forces, the force of tension pulling up and the force. The second one is a little bit harder, but once again, we've done this before, right? We have the force of gravity going straight down. We have the normal force perpendicular to the ramp. And then in this case, we have a tension force that is pulling the block. So these two diagrams should not be too challenging. Now for this block here, once again, we have this so the block is on a ramp, right? And so we have two forces that are parallel and perpendicular here. However, our force of gravity here is currently at an angle, essentially, 35 degrees. So what we want to do is we want to break down the force of gravity into parallel and perpendicular components. So the force of gravity here is our hypotenuse. So if we were to draw a right triangle here, this is the perpendicular, this is the parallel. The perpendicular side is going to be mg cosine theta. So the perpendicular side here is going to be mg cosine theta. And then this side here is going to be mg sine theta. So now essentially we've redrawn this free body diagram so that everything is either parallel or perpendicular. And the thing is, because everything here is in static equilibrium, the system is motionless, everything should cancel out. And in this particular problem, there's no friction because I said so. So there's no friction we need to worry about. Okay, so now we need to solve this problem here. We need to solve for the mass of block B. So why don't we just start with block B, set up block B first. So luckily block B is there's only one direction here. It's only going straight down. So we don't even need to set up things in terms of parallel perpendicular. So the sum of all forces for block B, in this case the y direction. What is the sum of all forces? Well, block B is motionless, so the sum of all forces is going to equal 0. The net force is going to equal 0. So all the forces need to balance out. So the force going up, the force of tension, minus the force going down, it's going to equal 0. Which is just a long-winded way of saying the force of tension, that force going up is going to equal the force going down. So, and this is because, right, the block B is motionless. So whatever force is pulling block B down needs to equal the force going block B going up. So this is just going to equal force of tension is equal to mass. Okay, so if we can solve this, we can solve for our mass. However, we have exhausted all we can for block B. This is all the information we can do here. In order to figure out our force of tension here, we're going to need to use the other side. So So for the 200 meter block, we have the parallel and the perpendicular span. However, as I'm looking at this now, we want to solve for the force of tension. So we should you'll find that we don't actually need to solve for anything in the perpendicular direction. So let's just solve for things in the perpendicular direction. We'll show you why we don't actually need to do anything here. So the sum of all forces in the perpendicular direction is going to equal 0 because once again the object is motionless, it's not moving. So everything needs to cancel out. So there's only two forces that we need to worry about. We have the force going up, essentially perpendicular up the ramp. So the normal force minus the force going down, which is mg cosine theta, which is another way of saying the force going up is going to equal the force going down. So m times g is 200, cosine is cosine 35, so the normal force is going to equal this. But we don't actually need the normal force. So this step is actually kind of extraneous. We actually don't need to do this. What we do need though is we need to solve for the tension force. So setting up the tension force here, it's the sum of all forces in the parallel direction is going to equal 0 as well because the object is in equilibrium. So the net force is going to equal 0. So the force going up the ramp minus the force going down the ramp is going to equal 0 because it's in equilibrium. So the force going up is going to equal the force going down. So we know what mg is, we know what sine theta is, so that means we now know what our force of tension is. So now that we successfully solved for the force of tension, what we need to do now is we need to now use this and plug this, our expression force of tension here, into our block B equation. So the thing is, the tension the tension is the same everywhere throughout the system. So the tension here is going to equal the tension here. So that means we can use our expression of tension here into our quantity equation. So what we get is that mg sine theta is equal to mg. Okay, here's the thing. These two mg's are different. This mg is actually 200. So 200 sine theta is going to equal our mass times gravity. For the first problem, what we have is reducing sine 35. 200 sine 35 is going to equal my mass times gravity. So what I end up getting is that what I end up getting is that the mass block here is 11.7. How does this answer change if angles change in centimeters? Well, we expect that the block B is actually going to be heavier because gravity will essentially be pulling down this block A harder, potentially. And so what we end up getting is that block B in this case actually has a mass of 19. Okay, so does anyone have any questions of what I did here?
Mr. Hu,
Yeah, go ahead.
when you could you please explain how you drew the free body diagram with the 35 degrees and the perpendicular and parallel? Because I think that it's just a little bit confusing the way it's rotated for some reason.
Okay, so let's take a look at this free body diagram here. Let me try to draw it in a better way this time. So we have a block that's coming in at essentially a 35-degree angle. Okay, so first off here, we always have the force of gravity going straight down, never at an angle. Because the block is, okay, because the block is on a ramp, right? The ramp is going to exert a supporting force that keeps the block from falling through the ramp. So there's going to be a normal force that is perpendicular to the ramp. Force of gravity going straight down as always. And because the block is on a ramp, and the ramp is going to be is trying to keep the block from falling through the ramp, it's going to exert a normal force perpendicular to the ramp. Now, this block here is also attached to a cable, the cable or a rope, whatever, that is pulling the block up. This can be a tension force that keeps the block up. So right now the block is on a incline. And we have this, the tension force, which is parallel to the incline, and then we have the normal force, which is perpendicular to the incline. However, our force of gravity here is straight down, which in this case is not parallel or perpendicular to the incline. So what we need to do is we need to decompose gravity into a parallel or perpendicular component. So force of gravity here is straight down. So what I'm going to do is I'm going to draw a right triangle here, with this side being perpendicular and this side being parallel. So in order to figure this out, we need to know what this angle is. So if we do our alternate interior angles, so because this angle is 35 degrees, and this first triangle is a right triangle, that means that this angle here has to be 55 degrees. Right, because this is a right triangle, the sum of our angles equals 180. So this angle here is a right triangle because the force of gravity goes straight down. So this is 35 initially, this is 55, which makes this one 35. So alternate interior angles, is that the thing? So basically when we draw something like this, the angle of the ramp here is just going to equal the angle of this triangle here. So if we want to figure out what the perpendicular side is, we need to use a little bit of trigonometry. So this is our angle theta. The cosine of this angle is going to equal my perpendicular force over my gravity. So that, in other words, mg cosine theta is going to equal our perpendicular force. And then the sine of this angle is going to equal my parallel side of my force of gravity. So my parallel force is going to equal mg sine theta. So now if I were to redraw my free body diagram, I'm going to erase this right here. What I get is that we're going to have a perpendicular force going through the ramp. That's mg sine theta. No, mg cosine theta. Apologize. This is perpendicular. And then we're going to have the force of gravity going it down. That is mg sine theta. So this will end up being what your free body diagram looks like, with our force of gravity decomposed into a perpendicular and parallel component, our normal force, and then our force of tension.
Got it. Thank you so much.
Okay. Hopefully that was better. Okay. So what we're going to do right now is we are going to continue with the problem we started last week. Actually, now that I'm looking at this, we'll still do this problem. But as I'm looking at this, I'm realizing that this problem is actually pretty similar to the one we just did, just with a few things changed. So I know we started it last week. I wonder if you tried it a little bit over the weekend, you can see how I might be doing it similarly or differently. So what I'm going to do now is I'm just going to draw the problem out and then start doing it step by step. So we have a block here. So the whole system here is at rest. We have a block on a table, essentially. It's being pulled by force of tension 1. Keeping the ball from moving. Then we have another force of tension here. That is at a 30-degree angle. So what we're going to do is we're going to draw a free body diagram for each of these objects. I'm first going to draw one for the ball. So the ball has a force of gravity going straight down. This free body diagram, we always use squares for everything. So for the ball, what we have is we have a force of gravity going straight down. The ball is also being pulled to the left by the cable, the left cable, the tension 1 cable. And then it's being pulled diagonally upwards at a 30-degree angle. And it's the second cable. Meanwhile, the other block, the block is being pulled down by gravity. The cable is pushing it up with a normal force. There's a cable pulling it right, the tension force. And then the block is not moving because the system is at rest. So there's going to be a frictional force keeping it to the left.
Your screen's really small again. We can't really see it.
Okay, so For the ball, we have the force of gravity going straight down, as always. We have a tension force going perfectly to the left. That's a tension 1 force. We have the tension force going up and to the right at an angle, 30 degrees, so that's tension 2. And then for the block, what we have here, the block is motionless, so we have force of gravity pulling it straight down, as always. The table is pushing it up with a normal force. We have the tension 1 force pulling it to the right, and then we have the frictional force keeping it left. And this, we know there's a frictional force because the block is not moving. And all these arrows should be roughly the same. Well, at least the arrow should roughly cancel out because the block is motionless. So we do not need to do anything with this block free body diagram because everything is already parallel and perpendicular. But for the ball here, we need to do something for this tension 2 force because that is currently at an angle. So we need to do a little bit of trig here in order to break down this angled force. So currently this tension 2 force is coming in at an angle of 30 degrees. So what we need to do is we need to figure out what is the X force here and what is the Y force here. So if the angle here is 30 degrees, that means the cosine 30 degrees is going to equal our adjacent, which is X, over my hypotenuse, which is T2. So my X force is going to equal T2 cosine theta. And then my sine 30 here is going to equal my Y force over my T2. So my Y force should equal T2 sine 30. So using a little bit of trigonometry, I can break down this diagonal force, the tension 2 force, into a horizontal and vertical force. Now, instead of a diagonal force for my ball, I can now have a horizontal force that is T2, what did I say it was? T2 cosine 30? And then a vertical force that is T2 sine 30. Now this looks a lot more manageable. Okay, so there are essentially two parts, well, there are two objects in this problem. So that means we need to solve essentially two sets of equations. One set of equations involving the block and one set of equations involving the ball. So what I'm going to do is I'm just going to separate the board here into block and then ball, block and ball. And for each one, there is going to be a parallel and perpendicular. And with the ball here, the ball is going to have a parallel perpendicular. Actually, let's actually write this as horizontal and vertical. I think that actually in this case makes more sense. So the block is going to have a horizontal side and a vertical side. And the ball here is going to also have a horizontal side. Okay, so the board looking a little bigger. Okay, so here's the thing, right? This system is at rest, which means it's in equilibrium, which means that everything needs to cancel out. So the sum of all forces here equals 0. Sum of all forces here is going to equal 0. The sum of all forces here is going to equal 0. The sum of all forces here is going to equal 0. So the net force everywhere is 0. As the sum of all forces in every direction is 0, everything is going to cancel out. Okay, so which one do we want to start with? So let's start with the ball. No, let's start with the ball. The ball is the better way to start. What I wanted is I want to show you that as long as you get started, you can still figure out things. So we're going to start with the block, and let's first start with your horizontal direction. So the sum of all forces in the horizontal direction is going to equal 0, which means that the force going right minus the force going left is equal to 0. So the force going right is going to equal to force going left. So the tension force pointing to the right minus the friction force going to the left is equal to 0. So that means the tension force going to the right is going to equal the frictional force going left. Okay, so that's it. That's all we can do for now. There's nothing else we can do to solve this. So what we're going to have to do is we're going to have to go to the next part, the vertical section. So similar idea, the vertical force going up, the normal force going up minus the force of gravity going down is going to equal 0. So which is just another way of saying the force going up is equal to the force going down. That means the normal force here is going to equal 40 newtons because the force of gravity is given to us, which is 40 newtons. So that means the normal force also has to equal 40 newtons. Okay, so we could use this, but as of right now, there's not anything we really need to do here. We sort of exhausted all we can with the block, right? We sort of reached the dead end with the horizontal force. We have the normal force of the block, but this isn't really useful for us right now. And so what we need to do now is we need to go to the ball. So we're done all we can with the block. We need to go to the ball now. So what we're going to do is we're going to first look at the ball. Let's go look at the horizontal side because that's what I'm feeling right now. So the sum of all forces in the horizontal direction for the ball is going to equal 0, which means that the force going right, which is tension to cosine 30, is here, minus the force going left is going to equal 0, which is tension 1, which is another way of saying that the force going right is going to equal the force going left. Because everything cancels out. Once again, we have exhausted everything we can for the ball. We don't know the tension force here. We don't know the tension force here. So, and we do know the angle, which is 30 degrees, but that in itself is not enough for us to solve this. So once again, we are at a bit of a dead end here. So what we need to do is now we need to look at the last portion here. And hopefully we have to hope that Mr. Hu gave us enough information to solve the problem. But luckily, Mr. Hu did give us enough information to solve the problem. So the sum of all forces in the vertical direction for the ball is going to equal 0, which means that the force going up, T2 sine 30, minus the force going down, equals 0, which is just another way of saying that the force going up is going to equal the force going down. Now, we do know what the weight of the ball is. Weight of the ball is 8 newtons. So tension to sine 30 is going to equal 8. If I remember correctly, sine 30 is 1/2. So T2 times 1/2 is going to equal 8. So that means T2 is going to equal 16 newtons. So now we have successfully found the tension of one of the ropes, the one on the angle. What we now need to do is we need to figure out the frictional force and the tension 1 force. So we can't figure out the frictional force yet because we need the tension 1 force, T1. So that means we have to use this equation here, the one we found earlier, to try to figure out our T1. So our tension 2 times cosine 30 is T1, and our tension 2 we found was 16. So 16 cosine 30 is equal to T1. And cosine 30, if I remember correctly, is √3/2. Equal T1. So this is H √3 is going to equal T1. And now we have our frictional force, tension force, and the one in the left cable, the tension 2 force in the other cable. So now we can use this tension 1 to figure out our frictional force. So since our frictional force is just equal to tension 1 force, 8 √3 is equal to that frictional force. Okay. So that is pretty much it. I honestly could have just not given you the weight of this block here, because that's actually unnecessary. So what we did here, we actually found the normal force here for the block. We actually didn't need this because we were trying to find the magnitude of the frictional force, not the coefficient. So we actually didn't need to know the normal force at all. So this step here is actually extraneous. We did it just because it's always good to just exhaust all the information we have. But now we have our tension forces and our friction force. Okay. Does anyone have any questions about this? Okay, so do we want to do another 2 object problem, or do we feel like we can move on? I just want to get a gauge here. I was planning on moving on, but I also don't want to throw you guys completely into the fire. So do we want to do like another 2 object problem, or do we want to move on? Okay, so let's, okay. Okay, so here is what I will do. What I am going to do is I am going to introduce the next assignment for those of you who want to move on. And then for those of you who want another practice problem, once I finish introducing it, we'll do another problem. So that way everybody gets what they want. Okay, so what we're going to do is I'm going to introduce the next assignment we're going to be working on. And then I'll do a practice problem for the rest of us. So don't worry. Okay, so what we're first going to do is I'm going to first talk about this next problem here. I'm actually planning on adding a part 3 to this. I have 2 parts right now. I think I'm going to add a part 3, but for now it's just part 1 and part 2. So this is, hold on, my whiteboard's not showing up. Okay, so this is called, the next assignment is called car alert. So if you know what life alert is, this is car alert. The next new big thing targeting people of the older generation, me. So let's say hypothetically you turn on your TV and then you see this commercial. Help! My car has fallen and cannot get up. We're sending help immediately, Mr. Who. See, protect yourself with Car Alert and you're never alone. Car Alert saves a car every 11 minutes. Wow, that's really impressive. So now, let's say hypothetically, let's say hypothetically that Mr. Who did not purchase Car Alert insurance. So what happened is Mr. Who's car has fallen in mud and cannot get up, cannot get out of the mud. And so let's say hypothetically that Mr. Who did not purchase Car Alert TM, trademark pending. So what we need to do is we need to figure out a way to get Mr. Who's car out of the mud by himself. So he is very limited in his material, in the stuff available. What he has is he needs to figure out a way to pull the car out of the mud. What he has is there is a very sturdy tree nearby. So let's say that the tree is like a redwood tree or something. So it's very strong. It's not going to break. And he has a rope that is also incredibly strong, which is made of adamantium or Kevlar or carbon fiber or nanotube, I don't know, whatever. And the rope was not going to break. And so you need to figure out the most effective way for Mr. Hu to pull his car out of the mud. Now, unfortunately, there are no other objects in the area that is helpful or useful for Mr. Hu to have, and he doesn't have anything in his car to help him pull the car out of the mud. So the rope itself is 10 meters long, but it has some stretchy capability. It can stretch a little bit. So it's by default 10, but it could stretch to be longer, right? And the distance from the car to the tree is 10 meters long as well. The car has a mass of 1,000 kilograms, and mud has a coefficient of static friction of 1.5. Keep in mind, this is the hard part. I can only exert a force of 150 newtons maximum. So you need to figure out a way for me to pull the car out of the mud if I can only exert a force of 150 newtons maximum. So that is your task if you are ready to move on. This is not a test of your mathematical ability. It's instead a test of your cleverness and how well you can use some of the stuff we learned. So you'll quickly realize that 150 newtons is not very much force. So then you'll need to figure out a clever way of using the stuff we have in order to pull the car out of the mud. So for those of you who want to move on, that's your task. The assignment itself is on Canvas. I think I also posted a link in the chat. So if you want to move on, you can do that. For those of you who want to do a practice problem, let me see if I can find another practice problem real quick for us to use. Let's see. Okay. Is the rope on the tree frictionless? Yes, you can ignore any friction from the rope itself. Yeah, you can ignore any friction from the rope itself. So what we are going to do here is, let me quickly copy and paste this problem here. It's not copying. Hold on. Where is it? Okay, so we're gonna do problem 5 here. Let me zoom in as much as I can. Okay, so we're gonna do problem 5 here for those of you who want to do a practice problem. So what we're gonna do here is there is a hanging 1 kilogram mass, which is M2, that is attached to a 4 kilogram block on the table. So if the coefficient of kinetic friction between the mass and the tabletop is 0.2, what is the acceleration of the blocks? So a hanging mass is attached to a 4 kilogram block on the table. If the coefficient of kinetic friction between the M1, the one on the table, and the tabletop is 0.2, what is the acceleration of the blocks? So for those of you who are doing this problem, who want to do this problem, here is what I will recommend. This is a 2-object problem. So when you have 2 objects, you will want to draw a free body diagram for each object involved. And you will also need to solve a set of equations for each object. So for those of you who are interested in the practice problem, I'm going to go through it. I think I'll try to do A, maybe B if we have time. So to start off with, what we should do is let's draw a free body diagram for each one. So for M1, we have normal force going up, force of gravity going down. We have the force of tension going to the right, then we have the force of friction going back. For M2, we just have two things. Luckily, we have the force of tension going up, and then we have the force of gravity going down. What makes this problem harder than the last one is the fact that we can no longer assume that the system is in equilibrium, because we are now assuming that the system is actually accelerating, which makes our life actually a little bit harder. Well, not a little, actually quite a bit harder. But luckily, we don't have to work with any angles. So the free body diagrams, and I think the overall setup should be a little bit easier. So let's first start off with M2, because M2 only has one direction. So the sum of all forces for M2 is going to equal M2's mass times the acceleration. So, and the reason why the sum of all forces is no longer equal to 0 is because the system is no longer in equilibrium, because it's actually accelerating. So the sum of all forces in for M2 is going to be the force of tension going up minus the force of gravity going down minus the force of tension going up. And I believe that's all we can do here, because we don't know the force of tension. So for the block itself, for M1, M1, the sum of all forces for M1 is in the y direction is going to equal 0 because it's not accelerating up or down. It's instead accelerating in a horizontal direction. So the sum of all forces in the vertical direction is going to equal 0, which just means the normal force is going to equal the force of gravity. So normal force is just going to equal 4 times 9.8, which is 39.2. That's for the vertical force for the block on the table. That's not hard. That's not the hard part. The harder part is looking at the horizontal force. So the sum of all forces in the horizontal direction here is going to equal the mass times acceleration. So the tension force from the right minus the friction force is going to equal my mass times acceleration. So my tension force minus, what was it, 0.2, 9.2 is going to equal my M1 times acceleration. So now what we have is we have a system of equations where we don't know my tension and we don't know acceleration. We have two equations for this. So if we do a systems of equations, we can then solve for our tension. So what I'm going to do here is I'm going to rearrange it so that my tension force is going to equal my M1 times acceleration. So what I now have now is I have the systems of equations, tension and acceleration. So once you rearrange it, you can then solve for your tension and your acceleration. So pretty much the general strategy for working with two objects is you draw two free body diagrams and you work with this where you set up equations for both objects. And hopefully you'll at some point you'll end up having a systems of equations that you can solve in order to solve for your variables. I realize we are out of time here, so I apologize that I'm not able to fully do the problem here. If you are interested in a fully worked out solution to this problem, you can just let me know and I'll try to figure out a way to work it out and show you guys. Other than that, that's it. You don't have to work on the assignment as homework. We will continue it on Thursday. If you have any questions for me, if you want me to talk to you right now, you can let me know and I'll do that. Otherwise, you're free to go. Yeah.
Thank you.
Thank you.
Thank you, Mr.
Thank
Hu.
you.
Thank you.